Welcome to the review for assignment 6.3, which is on Newton's law of motion. Mainly testing on F net equals to ma, that's Newton's second law, as well as Newton's third law on action-reaction pair. Now let's start with question 1. Question 1 was really well done. You have a 400 kg box tied to a rope, and then this rope is pulled up by the crane. So for the free body diagram, there are only two forces acting on the box. One is, of course, is weight, so the weight of the box. And the other one will be the tension, which is due to the rope. So if you want to write the longer name, it will be tension by the rope on the box. In this context, just stating as tension would be enough. Part B, if the tension is 4100 Newton, what is the acceleration of the box? So this is when we'll compare the forces acting on the box. The tension upwards is 4100. The weight, which is equals to mass times gravitational field strength, will be 4000, right? So there should be a net upward force and therefore upward acceleration. So since the force is in the upward direction, I should have the tension bigger than the weight, and therefore I take tension minus weight equals to ma. Then you just substitute the values and you get a 0.25 in the upward direction. Then you will see that it is quite common to link dynamics with kinematics. The box is initially stationary, so if it's stationary, that means the initial speed or initial velocity is 0 meters per second. If the tension of the rope is maintained at 4100, it also means that whatever you have calculated, the acceleration 0.25, this will also remain constant for the box. And this happens for 10 seconds, so that is the time. What is the box velocity at the end of the 10 seconds? That will be the final velocity v. So if you recall, we have our 4 equations of motion in kinematics. The simplest equation will be final velocity is initial velocity plus acceleration times time, right? So just substitute all the values in, you get final velocity is 2.5 meters per second. This was really well done. The slightly problematic part was actually this part. How high is the box above the ground at this instant? So I had a handful of you who did, distance is equals to speed times time. Take note that this is not applicable for this question because we can see that the speed increased from an initial velocity of 0 meters per second to a final velocity of 2.5. So it's not a case of constant velocity, right? So if velocity is constant, you can just say that, displacement is that constant velocity multiplied by time. However, in this case, velocity is increasing from 0 to 2.5, right? So you can see the area under the graph for these two cases are clearly not the same. Okay, so how do you solve questions like this? Of course, if you want to, you can sketch your VT graph and take half times base times height. So you end up with half times 2.5 and then times 10, right? Alternatively, just apply your equations of motion. Displacement is half initial velocity plus final velocity times time. You'll still obtain 12.5 meters. Part D, at the end of 10 seconds, now the tension is reduced to 3900. What is the new acceleration? So again, we compare the forces acting on the box. One is the tension upwards, 3900. One is the weight, 4000 downwards. So just by looking at these two values, we can conclude that the net force must be in the downward direction. So acceleration must be downwards. Right, so since net force is in the downward direction, I take the downward force minus the upward force equals to ma. Okay, and therefore acceleration is 0.25 in the downwards direction. Part E, almost all of you knew the answer. The answer is 4000, but almost half the class didn't show me any working. Okay, so working is important no matter how obvious it looks. as long as I give you this big space over here, we expect workings to be shown, okay? So what workings are we expecting? Read the question. It says, the box is lowered with a constant velocity. Constant velocity means acceleration equals to 0. That means the forces on the box are balanced, right? So T must be balanced by the weight. So minimally, you need to write this statement, okay? F net equals to MA, which is equals to 0. So this is the reason why T is numerically equals to weight, then equals to 4,000. Question 2. A lift moves upwards with an acceleration of 2.0 meters per second squared. Now, if it moves upwards and the acceleration is also upwards, that means when you draw the free body diagram for the lift, you must be able to show me that the upward force is greater than the downward force. So when you are drawing the free body diagram for this question, draw the tension slightly longer than the weight vector. So this is not the same as question 1. We go back to question 1 and take a look. Question 1 over here, you were sketching the free body diagram before there was any information given about the acceleration. So that means the marker will not be will not be looking out, okay, for the length of the force vectors as compared to this question, right? If acceleration is upwards, that means net force must be upwards. That means your upward force must be a longer vector than the downward force. Okay, so just check your answer. Make sure you draw it a bit longer. Okay, in fact, I can improve my answer a little bit, right? Just make it more obvious. All right, next. If the tension in the rope is 5.75 kilonewton, what is the mass of the lift? So again, looking at the information, right, given to us, I have acceleration, I have forces, I don't have the mass, then we should be applying F net equals to MA, where M is the unknown. So if net force is in the upward direction, I take tension minus weight equals to N times 2, okay? So from there, you should get a 479 kg. Everyone, please take note, okay? When you need the M for subsequent calculations, you should indicate for yourself more SF. What is the value of M? So that you can avoid rounding off error in subsequent steps. Okay, of course, in this particular question, if you didn't use 5SF, you probably will still end up with the same answer, 3830. But sometimes you may just end up with a rounding error where the third SF, the value may change, okay? So part C, now the lift approaches the highest floor. So when you take a lift to the highest floor, when you reach that floor, your lift must come to a stop, right? So therefore, it must decelerate or slow down. So as it is going up, direction of motion is up, right? And then it decelerates, it slows down. So acceleration must be in the opposite direction of velocity. So this question is really indirectly telling you that acceleration is downwards, so net force is downwards. So now if I compare the forces, tension, and weight, the weight vector must be a bigger force, right? So I take weight minus tension equals to M times 2. So like I said just now, I will substitute 5SF for my intermediate working, but for my final answer should be displayed to 3SF. Now, alternatively, I think this question was asked in class before. Okay, can you substitute acceleration as negative? Answer is yes, of course you can. Okay, so there were a handful of you who substituted your acceleration as negative. Now, what it tells me is that if acceleration is downwards, okay, and you substitute as negative, that means you were taking upwards as positive. So if you take upwards as positive, then tension, which is upwards, will be substituted as a positive force, and then weight, which is downwards, will be substituted as a negative force. So this group of students will have T minus mg equals to M times minus 2. So not to worry, if you take a look at this equation, right, and this equation where acceleration is substituted as 2, they are actually two identical expressions. Okay, just a rearranging of equation. Okay, moving on. Question 3. Question 3, free body diagram was also very well done. Okay, except there were a handful of you who overlooked this instruction. Okay, so if the boxes are pulled along a smooth surface, what it means is that there shouldn't be any friction at all in part A. Okay, so in part A, there's no friction. And then there's a rope over here. So both A and B will experience a tension which is directed away from the blocks. And then if you look at block B is also experiencing a force which is directed towards the right-hand side. Magnitude is given as 25 newtons. So we have to draw the free body diagram for blocks A and B. Now take note, if we say that we are drawing free body diagram, right, that means you must include every single force acting on the blocks. Okay, so not only the horizontal forces, but also the weights of the blocks. So weight of A, weight of B, and then because they're in contact with a floor, so the floor will also exert the normal contact force by the floor on the blocks. Since the two blocks are only accelerating in a horizontal direction, what it also means is that in the vertical direction, the forces must be balanced. So check that you have drawn the normal contact force equal in length to the weight for both blocks. So what was I also marking for? I was also marking for your tension, okay, acting on blocks A and B. They are along the same string, same rope rather. So these two tensions should be of equal magnitudes. And then on block B, okay, just draw this 25.0 Newton force. In the context of this question, we don't really know, okay, how the person is pulling block B with the 25.0 Newton force. So I will not name it as a tension. Okay, so you may not be, for example, pulling with a rope. Okay, so I will not name it as tension. I will just name it according to what is given in the question. Question states as 25. I'll just name it as 25 newtons. Part B was very well done. Okay, calculate the tension in the rope connecting the two blocks. So what we need to do, let's just consider, okay, one of the blocks. If I consider block A, net force on block A causes the mass of block A to accelerate, right? And these two blocks are connected and therefore they are going to move with the same common acceleration. So F net equals to MA, the only force in the horizontal direction for block A is the tension. So the tension causes a 3 kg mass to accelerate. I do not know the acceleration. Okay, I cannot solve two unknowns with one equation. So now I need to go to block B. So block B in the horizontal direction, the net force will be 25 newtons minus tension. I'm basically just considering the horizontal forces, right? So F net is 25 minus T. This causes block B of a mass of 7 kg to accelerate, right? So the M will be 7 kg and then to accelerate, that's A. Now if you look at equations 1 and 2, you'll find that equation 1 has a T and equation 2 has a minus T. Okay, just take 1 plus 2, the T will cancel off. So you have a 25 Newton net force is equals to the masses of the two blocks and then multiply by the acceleration. So A is 2.5 meters per second squared. From there, you can just substitute the value of A into equation 1 to solve for T. Okay, so this is what the question is asking for. Alternatively, I have shown this in class before, we can also consider blocks A and B as a single body. So this 25 Newton force is acting on this single body of 3 plus 7 kg, right? So this is actually the same as equation 1 plus equation 2. Okay, next. Now the question is changed a little bit. The blocks are now put along a rough floor. So if the floor is rough, that means there is friction, right? And then the question also tells you that the blocks are moving at a constant velocity. Constant velocity means zero acceleration, which means zero net force. So on each of the blocks, the forces must be balanced. Then the question asks you, can you now determine the friction between the block and the floor? Assume that the tension remains the same as in part B. That means if I look at this rope over here, okay, this rope over here is still a tension of 7.5 newtons, okay, within the rope. Okay, over here. So this tension 7.5 Newton, this tension 7.5 Newton. Now let's consider block A again. If I look at block A, the horizontal forces are only the tension and the friction, right? So since F net equals to MA equals to 0, then the tension must be equal to the friction, right? So the frictional force is 7.5 newtons. Now we look at block B. Again, in the horizontal direction, F net equals to 0, right? So rightward force, there's a 25. Leftward force, you have the tension of 7.5 and the frictional force of FB, right? So solve the equation, you get FB equals to 17.5. So this is 7.5 plus friction, then this is 25. Okay. Question 4. A man of mass 60 kg enters a lift of mass 800 kg. Okay, the man steps onto the weighing scale. Now this 800 kg is really just a distractor. Okay, you'll find that for the whole question, there was actually no need for us to use this information. Okay, so first thing, ask you to draw the free body diagram for the man. The man will definitely have his own weights. Okay, so this is weight of, take note, not the lift, okay, but the man. So weight of the man. And then at the same time, because he's in contact with the weighing scale, so there's a normal contact force by weighing scale on him. Part B asks you, what is the reading on the weighing scale? Okay, if the lift accelerates up and then accelerates down. So what we need to remember is whatever the reading, okay, on the weighing scale shows is basically dependent on how hard you press against it, which also means that basically reading of the weighing scale is the normal contact force, okay, by a person on the scale. And the normal contact force will be basically the action-reaction pair with the normal contact force by weighing scale on the man. I repeat, okay, the reading on the weighing scale is normal contact force by man on scale, which is an action-reaction pair, okay, with the normal contact force by scale on man over here. So if you can find this reading, you will know this reading. What if the lift accelerates upwards at 2 meters per second square? Now, if the lift accelerates upwards, then the man who is inside the lift will accelerate together with the lift. Okay, so if I look at the free body diagram of the man, okay, now that he is accelerating upwards, his normal contact force, or rather the normal contact force by the weighing scale on him must be larger than his weight, right? So taking upwards as positive, I get normal contact force minus the weight equals to m multiplied by 2. Okay, so rearranging, you should get 720 newtons. Next, the lift decelerates upwards. So what it means is while the lift is going upwards, that's the V, the lift is decelerating, right? So slowing down. That means acceleration is in the opposite direction. to the velocity, right? So acceleration is down also means that the weight must then be a larger force than the normal contact force, so that net force is downwards. Okay, so net force is in the same direction as acceleration. So now net force is mg minus n, and that causes ma, right? A is again 2 meters per second square. From there, you can calculate the reading is 480 newtons. Or in our daily lives, okay, the weighing scale usually show the reading in kg, right? So if our weight is 480 newtons, then the weighing scale, reading wise, it shows us a 48.0 kg. Okay, so for this part, we accept 480 newtons or 48.0 kg. Okay, for the previous part, we accept 720 newtons or 72 kg.